Hello everyone, this is Ashraf Mahgoob, and today I am presenting SimVecs, Similarity-based vectors for utterance representation in conversational AI systems. This work is a collaboration between Purdue University, DCSL Lab, and Microsoft. First, we discuss what is the modification for SimVecs. Conversational AI systems provide a natural way of interaction between customers and adaptive intelligence systems. Some examples of conversational AI systems are Cortana, Alexa, and IBM Watson. In these systems, the key requirements are to efficiently parse user queries and to understand the intent behind each query, and also provide an adequate response to users. Now, to meet these requirements, a natural language understanding service is usually integrated within the conversational AI system. This LU service uses machine learning methods such as classification, clustering, and semi-supervised clustering to meet these requirements. Now, an essential step is to provide an efficient utterance representation for every query in the vector space. The reason that makes this challenging is that in conversational AI systems, there is a diversity of domains and languages that needs to be supported. Conversational AI utterances are very short and sparse. Therefore, static vector representation is not able to provide optimal performance across diverse applications. Now, dynamic representation is needed, as the same pair of utterances can be considered similar in one application, but still different in another application. One example is the utterance, "I want a large pizza," can be of type "order food for a restaurant" application, while the same utterance can be of type "none," which is an outlier for a bus tracking application. Therefore, we propose a vector representation method called SimVecs that generates dynamic utterance level vector representations for different LU applications. Now, SimVecs provides a dynamic utterance level vector representation for different LU applications, and in each utterance, the representation is a vector of similarity scores to a set of automatically identified representative utterances. SimVecs combines several similarity metrics into a single overall similarity metric by the given equation. The given equation shows a multiplication between a weights vector W and 6 different similarity metrics, pairwise similarity metrics, such as unigram, character similarity, bigram similarity, trigram similarity, and the length of the utterances, as well as the word order. Now, we show an example of some utterances that map to different intents and the corresponding pairwise similarity metrics given the combined similarity metric that we proposed in the previous slide. So in this example, we see an example of 10 different utterances that belong to 5 different intents. And we can see that higher similarity is given to utterances that belong to the same intent. Afterwards, SimVecs uses every row in the pairwise similarity metric as the corresponding utterance representation for every utterance in the dataset. Now, to perform our evaluation, we compare to several baselines. The first baseline is bag of words, which performs the best among all baselines. In bag of words, vectors sizes are proportional to the vocabulary size. With the sparsity in conversational text queries, bag of words cannot capture adequate features of the utterance. Another set of baselines are pre-trained vectors such as sequence autoencoder and fast text. In this set of baselines, these vectors are trained using a neural network with a large corpus and billions of tokens, with such data being very rare in the conversational text domain. Utterances are too short for the model to learn efficiently, while pre-training on a generic corpus causes the vectors to become biased to the training data domain. The first case that we compare SimVecs in is unsupervised learning. And in this table we show purity scores for SimVecs versus other baselines. We see that SimVecs outperforms all other baselines except in just one corpora. In the second case, we compare SimVecs to other baselines in the semi-supervised learning task. And the x-axis shows the percentage of labeled data, the data that is manually labeled by the users, while the y-axis shows the purity scores. And as expected, the purity increases with more manually labeled data. But what we notice is SimVecs reaches the maximum purity between all other baselines with the smaller amount of manually labeled data. And in the third case, we compare SimVecs to other baselines in the supervised learning task. The x-axis shows different corpora and the y-axis shows the F1 score. We also see that SimVecs significantly outperforms all other baselines in this task. In conclusion, we introduced SimVecs, which is a similarity-based vector representation technique that is designed to overcome prior work limitation in the field of conversational AI. We discussed the main challenges in vector representation for conversational AI applications and how SimVecs overcomes these challenges. Through evaluation on different corpora and for different learning tasks, we showed that how efficient the vector representation generated by SimVecs over several baselines. Thank you very much.